Hi there, Chem Coach Powers here with another wonderful lecture on chemistry for our physical science kids. Today we're going to be talking about solutions some more, and specifically we're going to talk about what kind of things allow for solutions to occur and how we can make solutions dissolve or how we can make a solute get dissolved in a solvent faster. So let's go ahead and start with this. This is section 8.2, and let's look at our objectives. Today we want to look at how a substance dissolves, relate the structure of water to its ability to dissolve many different substances, and identify the factors that affect the rate at which a substance dissolves. So first of all, let's look at that structure of water. You can see here that we've got the slightly positive charge where the blue parts are on the water molecule. That's the hydrogen, and then the slightly negative part where the oxygen is. Okay, so this is a polar molecule. Water is a polar molecule, and that is a big part of why it dissolves things. Okay, in fact, we oftentimes call water the universal solvent, meaning that so many things dissolve in water, and that's because so many things are polar. Okay, water can dissolve an ionic compound, or can dissolve ionic compounds as well as polar compounds, right? Polar, by saying polar, what we mean is that there's two different parts to the molecule that have different properties, one being positive, the other being negative. If you thought about like a magnet that might have two poles, then you would think about the differences between the South and the North Pole, right? So polarity has to do with that same type of thing. When we're talking about a water molecule being polar, it means that one side is positive charge and one side is negative charge, and those charges are separated. Okay, and so what that does is that makes water have the ability to both attract the positive ions and the negative ions. So here's an example of that. If we look at water dissolving here, we can see that the water molecules themselves are kind of surrounding the salt. So if we look over here, and let me get my little pen going here. Sure. All right. I'm going to change my ink color. Make it pop and stand out really well for you. Okay, so you can see, not going to pop out on the white. Will pop out on the black, but not on the white. Okay, enough distractions there, Powers. You can see here we've got a water molecule, and it's approaching the salt crystal, and we've got other water molecules doing the same thing. What happens is these water molecules are orienting themselves so that they're able to align the positive sides, which are the hydrogen atoms, toward the negative sides of the sodium chloride, which would be the chlorine, which is negative, right? So you'll have these positive parts of the hydrogens all surrounding the negative chlorine. Look at that. You see how all of the negatives, all of the positives, which are here, right, in the water, have now surrounded themselves, and they're surrounded themselves. They're surrounding the chlorine, which is a negative charge. Okay, so this is a big negative charge, and all the positive parts of the water molecules are surrounding it. Now, what that does is that basically means that there's a lot of attraction there, and that happens while it's still on the molecule itself, right? So while it's actually attached to the molecule, these water molecules just come in and start yanking on it, and the multiple combined water molecules will pull on that part of that salt crystal and pull it apart. You'll notice that it's exactly the opposite here. How my negative, this is my negative part of my water, right? My oxygens are negatively charged. All the negative parts of my oxygen on my water are now surrounding the sodium, which has a positive charge. And so this is how water is actually going to look as it surrounds in this case, a salt crystal. It would do the same type of thing to other types of crystal that are polar. Might be a little bit more extreme with some things than others. Now, on the next slide here, we can see that we have a phrase that we want to make sure that we're very familiar with, which is like dissolves like. Basically, that means that polar substances are going to dissolve in polar substances. And likewise, nonpolar substances will dissolve nonpolar substances. Okay, so the reason something dissolves has to do with polarity. When you think about oil and water mixing, that classic example, it's not staying apart because of density, which is oftentimes what we think. That's not the case. It's staying apart because of polarity differences. Oil and water don't mix because oil is nonpolar and water is polar. Now, there are different densities, and the reason that the oil sits on top is because it's less dense than the water, but that's not why they don't mix. You can mix them together, switch them up a little bit, but then they are going to reestablish their original line of demarcation where there's not much dissolving going on there. Okay, so dissolving is, again, depending upon those forces between the particles. And if that combined forces of all those particles surrounding the solute particle, okay, is greater, then it pulls the little part of that solute particle away from the big crystal structure and it brings it into the solvent. Hydrogen bonding is one of the intermolecular forces that's present as water is dissolving something like sugar, for instance. Okay, hydrogen bonding is a strong intermolecular force, and it takes place when you have a hydrogen atom that's bonded to a highly electronegative atom of another molecule. And that's attracted to these unshared electrons of another atom, or another molecule. So for instance, in this case, what we're talking about is what we just saw the picture of there. We saw that hydrogen, okay, and oxygen were attached, and hydrogen bonding is the attraction between that hydrogen and, for instance, another oxygen that might be connected, on another place there. So that's hydrogen bonding. Now, let's look at what water is doing as it combines with a sucrose molecule. And again, you can see how the sucrose molecule now has, a positive side, okay, and a negative side. That's going to be a hydroxide group, right? Probably. And you're going to have the positive side of the water attracted to the negative side of the oxygen, and the negative side of the water attracted to the positive side of that hydrogen that's part of that sucrose molecule. And that happens in all sorts of different places, and that's what pulls that sugar molecule off of a big crystal or a big lattice of those sugar molecules. Now, you can watch this YouTube video. It's an interesting video that kind of shows you that dissolving process. And so if you want to watch the video, you can look at this PowerPoint online and then look at it that way. Or you can just type in that link if you'd like to. Okay. Why do substances dissolve? Well, again, the whole idea is that there's two things that are happening. One is that you've got this solvent, which is a liquid, which has got more energy, and it's imparting some energy into the solute particles, and that's enough to break up some of those intermolecular forces of attraction, okay? And also you have attractive forces of the actual particle of water, for instance, to the particle of the solute like sugar, okay? So now as we go into this next little slide here, I want to talk about three things that are going to increase the rate of dissolving. Okay, so you can speed up the rate of something dissolving in a solvent, a solute dissolving in a solvent. And what you're going to do is you're going to do one, increase the surface area of the solute. So you can see with the picture down below, we have a salt crystal. If it's 1 centimeter by 1 centimeter by 1 centimeter, you're actually dealing with 6 square centimeters of surface area. If you think about a process like that, okay, it's a cube, it's got 6 sides, right? And if you were to break that up into smaller little pieces that were just 1/10 of a centimeter big, then you're suddenly going to have 60 square centimeters of surface area. So breaking things up into smaller pieces actually increases the surface area very significantly. And this is, kind of present in all sorts of things. For instance, even in biological systems, this is why our cells need to be small to work as well as they do. A lot more gases can exchange, for instance, between cell membranes and the environment if we have small cells versus having large cells. Another way to increase the rate of dissolving is to increase the temperature. And again, what you're doing is you're increasing the number of collisions, right? And then you can stir the solution. Again, what are you doing? You're increasing the number of collisions between the solvent and the solute. And so that gives more opportunities for that solvent particle, that water, to have an attraction to the solute particle. And so that's why that works. All right, so this is another good video. If you want to type that into your browser, or if you have the opportunity to upload this particular video to your personal computer, then you can probably just click on that and it would work, or hopefully it will show up in this little screen there. All right, so one other thing I want to talk about before we wrap things up is the dissolving process. And, it's important to realize that if you put solutes into a solvent, then it can affect the way that solvent behaves. So for instance, if I put some salt into some water, it's going to change the boiling point. It's actually going to raise up the boiling point, because then it's harder for the water particles to escape because they have these solute particles in the way. And so as you add energy, not as many of them are escaping because they're hitting solute particles and they're staying in solution, or staying in the liquid. And then you can also lower the freezing point of solutions. For instance, you can look at ethylene glycol, which, if you think about your radiator in your car, this would be antifreeze. And the ethylene glycol, or at least a big portion of it, the ethylene glycol is going to basically make sure it's a solvent, the solute particle, that makes sure that the water doesn't get a chance to grab on and form these little ice crystals. So the water is trying to, form an ice crystal by bonding with another water molecule through hydrogen bonding, and that's not going to happen. Okay, so ethylene glycol is getting in the way of those bonds, and those really are intermolecular attractions, but in the way of those intermolecular attractions taking place. Okay, so dissolving can be something that will affect the physical properties of a solution. It's not a chemical change, but it does affect some of its chemical properties in a sense. Okay, so let's see what we've learned. Have we learned how to describe how a substance dissolves? Yeah, remember, talk about all those little collisions and all those little slightly positive and negative parts attracting and pulling things away from each other. Now, in a nonpolar situation, that description is a little bit different. We haven't talked about that, but that is not quite the same, because those nonpolar substances don't have the positive and negative sides to make things like that attracted to it. That's a whole other subject. And then, can we relate the structure of water to its ability to dissolve many different substances? Yeah, because it's polar, and so many things are polar. There's not very many things that we kind of encounter on a day-to-day basis that are nonpolar. So water is able to dissolve most things because most things are polar and water is polar. Identify factors affecting the rate at which a substance dissolves. All right, so we talked about the surface area, we talked about the temperature, and we talked about stirring being three great things that will affect that. So I hope you had a good time today learning a little bit more about things that dissolve, and hopefully you'll be able to use this in your real world, because you actually do deal with things a lot of times that are dissolving. And now you might be able to talk about why, you've got sugar left over at the bottom of your cup after you put a bunch of sugar in your tea, and you didn't stir it all the way. Or maybe it was cold tea versus hot tea. Yeah, all that kind of stuff. All right. Have a great day. Be kind to one another. God bless you.